Syah jela dia tak boleh buat macam tu. Dah contoh lah. Shoot another video lah.
Sini.
Dia jealous sebab dia dah ada rakaman dalam kita duduk sini. Jealous. Sini yang duduk.
Lain boleh kan?
Bakat. My dream. Bisa I go. This my dream. Jadi ada. Jadi.
PSE power system, PPE power electronic,
Oh, betul ni. Bisa kan?
PPE.
Oh. Maju. Certified. Mak aku bagi. Kau sikit. Kau mak lagi aku.
Assalamualaikum and good afternoon / evening. Right. Okay. So yesterday lecture, the 1 hour lecture, we did cover for this lecture number 2, which is on the power semiconductor switches and also power competition. So if I'm not mistaken, we stop somewhere around 12. Okay, we just recap. Okay, so for the power semiconductor switches, basically you are going to look into 3 groups of family. The first one is diode. Okay, we look back on the diode. Okay, so this diode is a unidirectional device. Okay, what does it mean by unidirectional device for a diode? Which is it only allow current to flow in one direction. So there will be an output during the positive region. When your circuit going to negative region, your diode will block the current from entering the negative region. So during the negative region, the output will be equals to 0. Alright, so this is for diode. Okay, and then for the SCR, so for the family of thyristor, we are going to look into SCR, which is a silicon control rectifier. So you are going to use this SCR on the topic of rectifier, which is it will convert from DC to DC. As for the next chapter, the next week on DC to DC converter, for switch, I believe you are going to use either MOSFET or IGBT, which is transistor family, the next family. Yeah? Okay, so for the SCR, okay, so this is the symbol for SCR. silicon control rectifier. Okay, SCR is also unidirectional device, which is it only allow current to flow in one direction. So it will block your current from entering the negative region. Okay, so for SCR it has three terminals, which is we have anode, cathode, and also gate. Okay, so now look at this gate terminal over here for this SCR. Okay, the anode will be connected to your positive terminal, which is your supply, and your cathode will be connected to your load. Okay, the gate terminal here will be connected to a gate drive, which is what we call this gate terminal. It needs a signal in order for this SCR to be on. Okay, for diode, you know that diode you have cathode and anode. As long as you give some amount of, you power up your circuit, then your diode will be on automatically. But for SCR, although your main supply is on, but you didn't give any signal to your gate terminal for this SCR, your SCR will not be turned on. Okay, so you need to give this signal to this gate terminal. So what kind of signal that you need to give in? Okay, so for this SCR or any other transistor family later, so all the gate terminal we are going to give in terms of pulses, and 0101 pulses. Yeah. So these pulses, you can generate these pulses from a pulse generator, a clock, or using microcontroller. Okay, you want the output that we want is pulses. Okay, 1010. So these pulses will be put into our gating terminal over here. Okay, if you are using simulation, okay, in software, in PSIM, there are two ways you can generate the pulses. Okay, one is using, later you're going to see during your lab session. One what we use is gating block. Okay, gating signal block. So this block will give a fixed pulses. However, you need to set how many pulses that you want in one cycle. If let's say that you want 3 pulses, you put it, number of switching point will be 3. Okay, so what are the pulses? It would depends on, let's say in PSIM. Getting block signal in PSIM. So basically they are setting that you can done. Okay, normally we are going to, the setting will be done over one period of time. Okay, one period, let's say your frequency is 50 Hz. So one cycle, which is one period of time, 1 over F, so 1 over 50, you will get 0.02 second. So 0.02 second is one cycle. Satu cycle, one complete cycle, which is if let's say that you have a sine wave, this one here. Okay, this is one cycle. Okay, so if let's say that you want 2 cycles, so you will have twice of this sinusoidal wave. Okay, and then if let's say that in simulation, let's say that you are required to simulate for 2 cycles, so you just multiply this. One cycle is, you know that 0.02, so you multiply by 2 in order to get 2 cycles. So you will get 0.04 second. So 0.04 second will indicate 2 cycles. You are going to simulate for 2 cycles, right? Okay, and then that one is for time. Okay, so for these pulses, in order for you to generate this kind of pulses, okay, we are going to look into one cycle. So one cycle 0 to 2 pi, which is 360 in terms of degree, 360 degree. Okay, duration of one cycle. Okay, let's say you want your pulses to be 2 pulses, which is this is 1 and 2, right? Pulses number 1 and pulses number 2. Okay? Right, let's say I put it somewhere around here. Okay. This is in PSIM, So how are you going to do this setting? So okay, this is when T on. Okay, when your switch start to when there is the first pulses, we name it as T on. And this is when the pulses become, which is your switch become open circuit, so it become T off. So this is for pulses number 1. For pulses number 2, also the same. This is T on 2, and this is T off 2. Right? Okay, that one is in terms of time. Now, in PSIM, the time, this T on and T off, need to be translated in terms of degree. Okay? So since, let's say, for example, here maybe the degree of for the T on time, T on 1, let's say I put it as 45 degree. Okay, and then it become off maybe around 90 degree. Okay, so that is the setting that you need to do for T on 1 and T off 1. For T off 2, let's say I make it's on around 300 degree, and then it will be off maybe around 340 degree, something like that. So that is how you do the setting in order to generate these 2 pulses inside PSIM software. Okay, this one here using getting block. Okay, there is another way. We use square wave getting block, square wave signal, so that the interval setting will be a bit different. So for the square wave, I will show you later during the lab session. Okay. Right. Okay. Now we go. This is how the from manufacturer point of view, this is how the SEL being packaged. So it has different packages, and it will depends on the application. Right. So we go for the family number 3, which is on the transistor. Okay, so for transistor, we have few types of transistor. We have BJT, bipolar junction transistor. We have MOSFET, which is metal oxide semiconductor field effect transistor, SIT, IGBT, and CoLMOS. Okay, right. So the most common transistor family is BJT, MOSFET, and IGBT. BJT is the oldest switch type for transistor family, and then we go for MOSFET. Okay, MOSFET you can use either in low power or in high power application. The only concerns with regards to MOSFET is in terms of frequency. So if let's say that you require very high frequency in your application, you cannot use MOSFET. Okay, you need to use IGBT here. IGBT is well suited for high frequency application. So high frequency which is greater than 10 kilohertz and above. Okay, so we go for the first family in the transistor, which is BJT. So BJT, it has 3 terminal. I think all you tak tahu kot you did learn during electronic devices kan? Ni kita recap je Right, so for BJT is a current control device. Okay, what does it mean by current control device? Adalah you need to supply sufficient amount of current at the base terminal over here in order for this BJT to be turned on. If you supply voltage, it will not be turned on. You need current. You need to supply base current. Okay, some amount of current. Okay, and the current flow will be from collector to emitter. So your collector will be connected to the input side, and your emitter will be connected to your output side. Right? Okay. Once you supply sufficient base current, then your switch here, your BJT will be turned on. If let's say that there is no base current being supplied, so your BJT will be off or open circuit. Alright. Okay, and then we go for MOSFET. Okay, this is the symbol for MOSFET. Okay, this one over here. This one when we have together with diode. Okay, this one here. Okay, so MOSFET is also 3-terminal device. We have drain, gate, and source. Okay, so the pulses here, the gating signal block over here will be connected to the gate terminal. The drain will be connected to your input, and your source will be connected to your load. Okay. Okay, so for MOSFET, it will be voltage control device, which is you need to supply voltage at the gate terminal. Okay, so the gate terminal over here for MOSFET, it has a threshold, which is it has the minimum voltage to be supplied for this MOSFET to be turned on, which is we call as threshold voltage VGTS, is it? Okay, this one, yeah. VGSTH, okay, which is the threshold voltage. So normally for MOSFET is around 1 to 4 volt. So you need to supply more than that in order for this MOSFET to be turned on. Alright, okay. Okay, once you supply sufficient amount of voltage at the gate terminal, okay, then your switch MOSFET will be turned on. So there will be a current flow between your source and your drain. Okay, if let's say that your supply less than 1 volt, maybe 0.5 volt at the gate terminal, then your MOSFET will remain off state. So this is the illustration for MOSFET. You can see here. Okay, the black box here is the switch. The metal plate behind your MOSFET is what we call as heat sink or the protection. So that is how the heat being released from your MOSFET. Okay, ini this one here apa? What kind of device? Okay, capacitor. Okay, resistor. I think this is also resistor. Right. Okay, and then this is the IV characteristic curve for MOSFET. Okay, I believe you know all this. Okay, this is we have this multiple line over here depend on the threshold voltage. Okay. And then for MOSFET, it has 3 regions of operation. We have saturation, and then we have breakdown and cut off. Okay, we want our switch to be operated in saturation region. Okay, this is the active region. We don't want our MOSFET to be operated in breakdown as well as in cut off. Okay, so first we are going to look into the operation for MOSFET, which is in the cut-off region. Okay, so when cut-off region is when our drain to source voltage will be close to your supply. Okay, which is VDD is your supply, supply voltage. This is when your VDS, drain to source voltage, will be close to your supply voltage, which is during this time your switch will be open. Okay, ataupun off, right? Sorry. Okay, and then for the second region, which is on the saturation region, okay, this is the active region that we want. This is the region that for all the switch to be operated. So this is when we apply sufficient amount of voltage, which is exceed our threshold voltage. Then there will be a current flow from your drain to source. Then your switch will be operated as an closed circuit, which is there will be a current flow. Okay. Okay, we have breakdown. Another one is breakdown region. Okay, now we go for the IGBT. Okay, so for IGBT, this is this one here is the symbol for the IGBT. Right, so again for IGBT we have also three terminal. We have collector, gate and emitter. Okay, this IGBT is a voltage control device, so which is you need to supply sufficient amount of voltage across your gate terminal for this IGBT to be turned on. Okay, so the difference between MOSFET and IGBT. Okay, for MOSFET, MOSFET is a bi-directional device. I think tahu kan? MOSFET is a bi-directional device, which is it allow current to flow in both region, in positive and negative region. IGBT is unidirectional device. So unidirectional, one region saja, which is during the positive region. So during the negative region, the IGBT will block the current from entering the negative region. Okay. Alright. So this IGBT, the creation of this IGBT basically it combine the characteristic from MOSFET and BJT. It take all the features from MOSFET and BJT, combine it together, become IGBT. Okay. So due to that, so it has very good in it able to allow very high current. And it has very low saturation voltage, so it's very hard to break down for IGBT. Okay. Right. Okay. This is also the advantages of IGBT, which is it has high voltage capability. The on state, which is RDS on, is very low, which is the internal resistance for the IGBT. So the lower the RDS on, the better the device will be. Which is you only need because you know right, for circuit electric circuit, for high impedance and low impedance, the current will go more to low impedance path as compared to high impedance path, right? So due to that principle, so for IGBT it will have very low RDS on, so it has a very low impedance. So there will be more current flowing to IGBT as compared to BJT. Okay. Okay, and then it has very fast switching speed, which is it can turn on and off the pulses. For the IGBT is very fast, so it's very suitable for high frequency application. Okay, high frequency application normally we use in path width modulation. Okay, path width modulation. Pernah dengar ke tak pernah dengar? Okay, path width modulation, you will DC to DC, I'm not too sure, but inverter later somewhere towards the end of the semester when I cover on the inverter topic. Okay, so basically let me draw the inverter. say for PWM, okay, this is an inverter. Okay, let's say this one here is for inverter, we convert from DC to AC. So the load part will be AC, the input part will be DC. DC, it can come from the fixed, which is power supply, DC power supply, or it can come from the renewable energy sources. Let's say from solar panel, from the wind turbine, and so on. Okay, and then it will go to this block of inverter. So this inverter is actually a connection of switches. Okay, in this case, let's say this is three-phase switch. So you will have a three-phase inverter, so you have 6 switches inside here. But I only represent as one. Okay, so there are 6 switches that will be connected for this three-phase system. And then you have, this is your filter, which is we have second order low pass LC filter. And then this is your load. Okay, your load, you can have R load, you can have inductive load, and any type of load, no problem. Okay, so since you have these switches over here, and you know that this is IGBT, it has 3 terminals and it has gate here. So this gate terminal, you need to power up the gate terminal in order for your switch to be on. In order for the current flow for this switch to be, there is current flow, right? Okay, in order to power up this gate terminal, you need to supply pulses. This one here. Okay, these pulses, okay, just now I show it what we call as a getting signal block, which is it gives you a fixed pulses. Fixed pulses, which mean that dia punya turn on and turn off time will be the same. The pulses we have equal with okay, this is T on, this is T off. Okay. Fixed pulses, which means that the T on will be equals to T off. It has the same duration, amount of switch to be on and amount of switch to be off will be the same. Okay, that is what we call as fixed pulses. Fixed pulses. Okay. Okay, can we vary these pulses? Okay, we can vary these pulses over here. Let's say we want to place at anywhere. Let's say you want to turn on for maybe 0.5 seconds, and then you want to off for 0.2 seconds, and then on back for 0.7 seconds. Okay, how to do that? How to make these pulses become flexible? So we are using this PWM, what we call as pulse width modulation. Okay, so for pulse width modulation, okay, pulse width modulation is actually what is inside this PWM. It actually consists of this this signal. This is comparator and the output. Okay, these two signals, we have what we call as a reference signal or VREF. Later you will see during inverter. Later I will show it again. And we have carrier signal over here. Okay. These two signals will be compared, will be fit into a comparator. Okay, what the function of comparator? Of course, it will do compare. It will compare, right? So it will compare between the high and low, which is if let's say that we have sine wave and also this is a triangular wave. So compare, which is it will be in one plot. So let's say you have sine wave over here, and then you have your triangle wave, something like this. So this is how it being compared inside this comparator. So for each intersection point between the reference and the carrier, which is between the sine wave and your triangular wave, there will be an output. So there will be a pulse, whether it's 0 or 1. Okay. So these pulses, it will depend on the rules. We have the switching rules. That one we will look into that later. Okay, so from that switching rules, we do the comparison in order to identify whether this is the output is 1 or 0 based on the switching rules. So let's say we have the output already, which is this 1010 over here. Okay, so this output from this comparator will be fed into our gate terminal of your switch. Okay, right. And then PWM, it require high frequency. Where do this frequency inside this PWM is from this carrier signal. Your reference signal will depends on your output frequency. Let's say in Malaysia we use 50 Hz as our output frequency, right? So the frequency for your reference signal will be 50 Hz. Okay, you cannot change that. Fixed at 50 Hz. Okay, the carrier signal. Okay, this is high frequency signal. So you can vary the frequency. You can use maybe 1 kHz. You can use 20 kHz. You can use in fact 1 MHz. It can be any frequency, but it need to be high frequency, more than multiple of 50 Hz. So the smallest is 1 kHz, and you can go beyond that. So that is why this PWM for the application of PWM is require high frequency, because the needs for this carrier signal, you need to have high frequency. Okay, so details about this later we will look back once we touch the inverter topics. Okay, and then we have okay, variable speed control. Variable speed control normally for motor, and also SMPS is for switch mode power supply. Okay, the next week you are going to cover for DC to DC converter. So DC to DC converter, also known as switch mode power supply. Switch mode power supply, which is a power supply, so the output will be DC. The input also will be DC. Okay, and then this is for the inverter. Obviously, you are going to use more IGBT for inverter. Okay, because of the PWM that need IGBT. Okay. Alright, so I already mentioned IGBT is a unidirectional device. It only allows current in one direction. Okay, okay. Now we go for these are the recent switches where we have the silicon carbide power MOSFET, gallium nitride. These two is the newest technology, which is it use a new substance, a new material, which is it use silicons and carbide as well as gallium nitride. Okay, these two is very powerful in terms of switching for high power application. It's better than IGBT, it's better than MOSFET. Okay, right, and then okay, the characteristic of emerging transistor, which is this, which is the silicon carbide and gallium nitride. The advantage, it has very high fast switching. It has low reverse recovery, low RTS on, and low gate power consumption. Okay, here, which is this one over here. Mana MOSFET? MOSFET is being invented 1976. IGBT a bit young, which is 1983. Mana BJT? BJT is 1960s. Wow. Diode mana? Oh, diode way before. Sebab we have thyristor is 1956. Diode is before that. Okay. Alright. Okay, so this is the summary. I think the comparison between the power transistor family, which is the BJT, MOSFET, and IGBT. Okay, now any question? Ada soalan? No. Ada. Alright. So we go for the second part, which is on the power computation and analysis techniques. Basically, all these terms to get you familiar back on the terms that we are going to cover, which is we are going to look into the sign convention, periodic table. What is periodic table? Periodic waveform. Sorry, to ingat chemistry lah. Effective value, average power factor, small ripple approximation, and the separation of DC and AC component. Okay, we look at the sign convention. I think you all dah ikut. Okay, so if let's say that you have passive component, this is how you represent the component. Regardless whether it's a resistor, inductor or capacitor, you just put it in a box. And then this is how the current flow and the voltage across, you need to place the voltage across your passive components over here. Okay, current will always measure in series, voltage you need to measure in parallel. I think you tahu kan? Okay. Okay, so for power source, which is whether it's DC or AC, okay, this is how you write the current flow. Current flow will going out, not going in. Okay, passive component, the current will going into the component. For power source, will be going out. Right, and then we have a periodic waveform. Okay, periodic waveform, which is, it has the same magnitude from within a cycle, within a period, you will have the same magnitude, the same shape and the same magnitude. That is what we call as periodic waveform. If you do not have that kind of shape and the same magnitude, that is what we call as non-periodic waveform. Okay. So for this waveform, it will consist of DC and AC component, and normally we need to use Fourier series in order to explain the waveform. Okay, right. So from that periodic waveform, just now we have this periodic waveform is actually DC component, which is your average value. Together with AC component, we combine it together, it become, the shape will follow the AC components here. Alright? So if let's say that you have this Fourier series expression, okay, Ft will be equals to A naught. Okay, the fundamental, the initial component inside your Fourier series expansion or Fourier series expression will be your DC quantity or average quantity. Okay, the one that you have the summation, the integration, derivation, and all that, that is AC component. Okay? Right, so in terms of RMS, which is effective value, so RMS, which is a sum of all the periodic table for over the cycle. So the summation, you get the RMS. Okay. Right, and then we have average power. Okay, we have instantaneous power, which is the power that we measured at that instant of time. It will not be the same as average power. Average power is a collective power that been calculated over one cycle. Okay, instantaneous. Let's say you have a circuit and then you run for 1 second. Okay, and then it stopped at 1 second, and then you do the measurement. So the measurement will be instantaneous power, which is, it will measure at 1 second. Okay, if let's say that you want average power, which is collective power from 0 up to 1 second, you need to have another measurement. You cannot depend on the scope. Normally, the scope will measure the instantaneous power or instantaneous voltage or instantaneous current. Okay, using the scope. Okay, ammeter ke, voltmeter ke, power analyzer ke. So for average value, it will be collective. Okay, that one you need to measure. You need to take at few times, maybe T1, T2, T3, and then you sum up to get the average power. Or in simulation, it has a function to give you the average quantity. Okay. Okay. In term of average, okay, which is this one here is average power, which is P will be equals to VDC multiplied by I average. Okay, VDC dekat sini is not DC voltage, the average voltage. Okay, normally average voltage is also known as DC voltage, but it's not DC per se. DC here, okay, is average voltage. Right, and then, okay, if let's say that your voltage and current, they are sinusoidal, so you can use this power equation. P will be equals to VI, V multiplied by I multiplied by cos theta over phi. Okay. Okay, that cost is to define as power factor. So if your voltage and current they are in phase, okay, which is if your current and voltage they are in phase, which is your load here must be resistive load. Okay, so your power factor will be equals to 1, which is unity power factor. Okay, if your load here is, let's say you have inductive load, inductor only, capacitor only, or combination of resistor and inductor, which is purely resistive load, then your power factor will not be equals to 1, it will be less than 1. And then your voltage and your current, if let's say that you see from the oscilloscope or from your simulation plot, it will be not in phase. Okay, in phase, which is it start and ending together. The signal will start and ending together. If let's say that the voltage, the waveform is not in phase, which is one will end before or after, so it will be leading or lagging power factor. So it depends on the value of the the inductor or capacitor inside your load here. How heavy or how high the value of your inductor and the value of your capacitor. Okay. So if let's say that you need to calculate the average power, okay, average power, if let's say that you have RL load, okay, for average power you need to only consider the value, if let's say that you do the calculation, consider R only. Okay, for average power, even though you have RL load, okay, let's say your R is 10 ohm, your L is 10 millihenry, okay. To find the average power, you need to, let's say your P will be equals to V multiplied by I. Okay, let's say you want to find your I, itulah you guna Ohm's law. So Ohm's law, V equals to IR. So that R, you only take the R untuk average power. Okay, only R. Even though you have inductor here. Okay, so that is how you calculate your power, the average power or DC power. Okay, and then we have apparent power. Okay, which is apparent power is measured in volt ampere. Okay, and then this is the equation for your power factor. Okay, this power factor down here, the equation for this power factor, it relates to the THD there. That THD we call it as total harmonic distortion. You are going to look again on this equation when we dealing with inverter later. Right? Okay, so this one here, all these factor, we have distortion factor, form factor, price factor. This will be used during rectifier. Okay, where this is what we call the factor that identify the quality of the waveform. Okay, distortion factor, form factor, and price factor. And then the last one is total harmonic distortion. Okay, this one here is normally measured in terms of percentage. Okay, THD here you can calculate or you can measure THD for voltage or THD for your current. Okay. So this THD, total harmonics distortion, which is, it means that how high your waveform is being distorted. Let's say you calculate the THD and then the THD that you get is 30%. So you can expect that when you see the waveform, it will be a bit distorted because of the percentage is quite big. And then if let's say that you do the calculation, the THD is let's say 5%. So you will expect the waveform will be a bit smoother. It will close to AC signal. Okay, that is how we look at the value of the THD and then we reflect back to the waveform. Alright, and then we have this is what we call as small ripple approximation. Okay, so for this small ripple approximation, you will look more when you do the DC to DC converter topics, which is on the finding the sizing for the capacitor. Okay, in order for you to find the value for the capacitor for DC to DC converter, you need to take into the consideration the percentage of the output voltage ripple. Okay, which is we are going to look this ripple approximation. So this output voltage ripple, percentage of this output voltage ripple, normally we need to use either 1% or 2% in order to find the value, the suitable value for your capacitor. Okay, that one later during the DC to DC converter. Okay, okay, and then we have the KVL and KCL. I think you all know the meaning of KVL and KCL. All the circuiting current will be some of the circuiting current will be equals to 0, and also for the that is for KCL. And the KVL, some of the voltage also will be equals to 0. Right? Okay, and then we are going to look into capacitor. Okay, we know that the basic function of capacitor is to store energy. Okay, so to store energy, and this capacitor is a voltage. Is a voltage quantity. Okay, you know capacitor store energy, inductor also store energy, right? Inductor is a current element component, capacitor is voltage element component, okay? So which is the changes with regards to voltage for capacitor, it will affect the value for the capacitor. It does not bother on the changes for the current. For inductor is a current control component. Bukan current control, is saya lupa term dia. Tapi it will affected by current. When you have changes in the current, then it will affect the value for your inductor. Okay, for capacitor, so the energy stored will be W will be equals to half multiplied by C, which is the value for the capacitor, multiplied by voltage across capacitor square. Then this is for the if let's say that the capacitor you're going to view the capacitor voltage in terms of waveform, and this will be the waveform for the capacitor voltage. You are going to look into this in DC to DC converter, because in DC to DC converter we have inductor and the capacitor connected together for that converter. So we are going to look into the voltage across the capacitor waveform, okay, and as well voltage across the inductor. How the response for the capacitor and inductor. Okay. Before that, okay, for this is periodic steady state, which is steady state waveform. So for steady state waveform, the average power will be equals to 0 for capacitor. If let's say that you have a non-periodic, non-steady state or transient waveform, the average power across your capacitor will not be 0. Okay, that is the difference. Okay, and then we go for the inductor. Inductor, the main function is store the energy. So what if let's say you have inductor in your circuit over here? Okay, you cannot expect that it will change instantaneously as you power up your device. Okay, it will take time to increase, okay, to store and release the energy. So it will take time. It will not immediately become 1 or immediately become 0, right? Okay, again for inductor is a current element component. Okay, this is the inductor current, the waveform. Okay, if let's say that the periodic or steady state waveform, the average power for the inductor will be equals to 0, same as capacitor. Okay, if let's say that for non-periodic, it will not equals to 0. Okay, that's it. Okay, so that's it. ada lah. Okay, so this is the last slide. Right, so nothing much. Basically, it's a revision. You will. Okay. Sila. Okay, so write down your name and your matrix number for today's attendance. Boleh ke? Apa dia? Line slow. Kalau nanti saya kalau tak boleh je nanti I will share in the group Luckily, it's not raining yet. Not yet raining. So selamatlah. All the riders selamat
Yeah.
Okay. So make sure you be able to fill in, scan the code and fill in the attendance link. So if let's say that you have any problem, do let me know so that we'll share the link in the group. Okay. Any question? Ada soalan? Any question in regards to this lecture material? Ada? Ada? Okay, so if I say there is no question, so I will end the lecture. So thank you everyone for staying in despite of the weather, unpredictable weather. So I see you guys during the live session. And next week, Mr. Nur Jasmine will take my place to teach you on the DC to DC computer. I will meet you guys again in week 15. Okay? Week 15. Okay, so thank you. Assalamualaikum and have a good day.
Jangan nafsu.